this equation here gives us a way to find the K sub P value if we only had the concentration value. So we have a Kc, and we can now calculate Kp. This equation tells us that the Kp equilibrium constant value is equal to the K sub C equilibrium constant value times the universal gas constant R multiplied by the temperature in Kelvin, those two raised to the delta N power. So what do each of these things represent? This is the gas constant, and you remember that from previous lectures, 0.08205 liters atmosphere over Kelvin mole. T is the temperature. And as with many things in chemistry, the temperature must be in units of Kelvin. This delta N is simply the change in the number of moles between the products and the reactant side. So in this case, this would be the product moles minus the reactant moles. So let's see how we could find the K sub P for the Haber process if we had the K sub Z value already. So assuming we had K sub C, we would take that value multiplied by the value for R times the value of T at whatever temperature we wanted to work. But now we have the issue of this delta N. What is delta N for the Haber process? So let's look at what delta N represents. It's the difference in the moles for the products and the reactants. In the Haber process, we have 2 moles of gas on the product side. So delta N is equal to 2. But then on the reactant side, how many moles of gas do we have? We have 1 mole of nitrogen gas and 3 moles of hydrogen gas. So that's a total of 4 moles of gas. So 2 minus 4 tells us that our delta N value is -2. So if we have the K sub C value, we can multiply that by R times T raised to the -2 power, and that will give us the K sub P value for our Haber process.